In a groundbreaking discovery, the James Webb Space Telescope has delivered an image that's causing a seismic shift in the world of physics, effectively ending a long-standing debate. This image, according to renowned astrophysicist Neil deGrasse Tyson, has shattered previous notions and is reshaping our understanding of the cosmos. It's not a matter of if this discovery is significant, but rather, it's become a question of when its implications will fully unravel and reshape our understanding of the universe. Join us as we delve into how the James Webb finding ends debate in physics' shattering image. Unprecedented insights into early universe with JWST. In the past 100 years, one of the most incredible achievements in studying the universe has been creating the Standard Model. This model describes how the universe has changed and what it's like now. It's mainly based on Einstein's theory of relativity and helps us understand how the universe has grown, including how it's expanded and how big structures in space formed. Within this model, several known components shape the cosmos. These include dark energy, the mysterious force driving the universe's accelerated expansion; dark matter, an enigmatic substance interacting weakly with light and matter yet constituting a significant portion of the universe; normal matter composed of familiar particles like protons and neutrons, neutrinos, elusive particles with minuscule mass and neutral charge; and photons, the fundamental particles of light. The universe sprang from the searing hot Big Bang approximately 13.8 billion years ago, preceded by a period of rapid expansion known as cosmic inflation. This inflationary phase created minute density fluctuations that later formed the basis for the formation of cosmic structures. However, recent scrutiny has turned towards this long-standing model. While it has served as the cornerstone of our comprehension of the universe for the past century, it's now under a critical lens. Despite robust observational support, scientists suspect that this model might be incomplete. As astronomers gather more observational data, each new piece of information undergoes rigorous examination within the context of the established model to test its consistency and validity. The advent of advanced tools like the James Webb Space Telescope has provided astronomers with a potent instrument, yet it's also presenting challenges to the Standard Model. The JWST's capabilities have opened new vistas into the early universe, disrupting some of our prior understandings. The story begins in the infancy of the cosmos, around 380,000 years post-Big Bang, when neutral atoms began forming. Roughly 550 million years later, a crucial event occurred known as reionization, during which most of the universe transitioned into an ionized state. The initial stages of reionization commenced approximately 200 million years after the Big Bang, potentially marking the emergence of some of the first stars. The JWST, with its unparalleled ability to peer deeper into the cosmos, has unveiled galaxies from more distant reaches than previously feasible, offering unprecedented insights into these early cosmic epochs. The Standard Model of cosmology, referred to as the inflationary hot Big Bang, or Lambda CDM model, has stood out for its remarkable success in explaining various fundamental aspects of the universe. This comprehensive model has elucidated phenomena such as gravitational lensing, the intricate structure of the cosmic web, the growth of cosmic structures over time, as well as the internal and relative motions of galaxies within groups and clusters. Additionally, it has provided insights into features observed in the cosmic microwave background, a relic radiation from the early universe. According to this model, as we peer further back in time and across cosmic distances, galaxies observed should inherently appear smaller, bluer, less developed, and possess fewer heavy elements. This prediction aligns with the expected evolution of cosmic structures over vast periods. It also suggests that at a point beyond our current observational capabilities, we would encounter what's referred to as the universe's dark ages, an epoch devoid of visible stars or galaxies, marking a significant transitional phase in cosmic history. However, as scientists rigorously scrutinize the integrity of these explanations, they've encountered conflicting evidence, leading to a state of crisis in cosmology. Despite the model's significant explanatory power, some observations and data don't seamlessly align with its predictions. This discrepancy between the theoretical predictions of the lambda CDM model and the actual empirical data has stirred a growing uncertainty in our understanding of the universe's fundamental workings. This discrepancy manifests in various ways, such as unexpected structures observed at cosmic scales, discrepancies in the distribution and behavior of cosmic elements, and anomalies in the patterns of the cosmic microwave background. These inconsistencies challenge the model's ability to comprehensively explain the observed universe, raising profound questions about our current understanding of cosmic evolution and structure. Deciphering the age of the cosmos. The cosmos holds mysteries that puzzle even the brightest minds. One of these enigmas revolves around the age of the universe. Pinpointing this age is a task that challenges cosmologists. The methods employed to measure this vast expanse vary, leading to differing outcomes. Understanding why these methods yield divergent results stands as a formidable quest for scientists in this field. One such method delves into cosmic background radiation. This radiation serves as a relic, preserving traces of the universe's early epochs. To unlock its secrets, scientists embark on a journey through the universe's expansion history. At the heart of this quest lies mathematical modeling, a tool reliant on Einstein's general relativity theory. This theory forms the bedrock for the Friedmann equations, essential in comprehending the universe's composition. These equations interlink elements like dark matter, dark energy, radiation, and more with the universe's expansion rate across different temporal milestones. By scrutinizing these cosmic constituents, scientists aim to unveil the age of the universe. Among the pivotal instruments aiding in this endeavor is the cosmic microwave background. Originating from the universe's nascent phase around 380,000 years after its inception, this CMB serves as a cornerstone in the pursuit of understanding the universe's composition and evolution. Detailed maps of the CMB, meticulously crafted through missions such as the European Space Agency's Planck mission, offer intricate insights into the universe's constituent elements. However, a challenge emerges with these maps. They lack comprehensive data on dark energy. This crucial entity, although negligible in the universe's infancy, now plays a pivotal role in its current state. Dark energy's absence from early universe dynamics necessitates scientists to manually integrate its effects based on other observational data. Despite this shortfall, scientists leverage the Friedmann equations to deduce the universe's expansion rate at distinct junctures in its timeline. The ability to discern the universe's expansion rate, not only in the present, but also across different temporal epochs, empowers scientists to derive the age of the cosmos. This multifaceted approach enables the determination of the universe's age today, providing a glimpse into its extensive history and evolution. Another avenue to unravel the universe's age involves a celestial spectacle, Type 1 supernovae. While the cosmic microwave background furnishes a comprehensive historical account of the universe's composition billions of years ago, observing the universe's expansion rate directly stands as another method. Type 1 supernovae, a cosmic drama where a star transfers its atmosphere onto a nearby white dwarf, eventually leading to a cataclysmic explosion, serve as crucial indicators for cosmologists. These supernovae, consistent in their behavior across the cosmos, are regarded as standard candles. What does that mean? Essentially, scientists have a firm grasp on their expected brightness, enabling them to estimate the universe's expansion rate during the time of these supernova events. By comparing this anticipated brightness with their observed luminosity, researchers derive valuable insights into the expansion dynamics of the universe at specific points in its history. This method, pioneered in the late 1990s, significantly contributed to the discovery of dark energy, an elusive force shaping the cosmos. It emerged as a cornerstone in cosmological measurements, offering a unique vantage point to explore the universe's expansion dynamics. Dark matter, dark energy, and the expanding universe. The Hubble constant acts as a ruler of sorts, measuring how the universe has been stretching since its inception in the colossal explosion known as the Big Bang, which occurred roughly 13.82 billion years ago. Imagine the universe as a balloon inflating steadily, but not at a constant pace. Over time, it's not just growing but gaining speed, like a car gradually accelerating on a highway. NASA's discoveries here aren't solely about this expansion rate. They're about what this rate implies. If the expansion slows down, it hints at a mysterious force, possibly dark matter, that's applying the brakes. On the flip side, if the pace of expansion speeds up, it might be due to something called dark energy, essentially stepping on the accelerator. Now, in January 2018, scientists stumbled upon something fascinating. While observing through various powerful telescopes, they noticed something peculiar about this expansion rate. It's not uniform. The Hubble Space Telescope and the Gaia Space Telescope observed a faster expansion of about 45.6 meters per second per megaparsec in the nearby universe. However, the Planck telescope recorded a slightly slower expansion of 41.6 meters per second per megaparsec in the more distant reaches of the universe. Edwin Hubble, after whom the Hubble Space Telescope is named, was the one who initially proposed this concept of an expanding universe. Back in 1929, this American astronomer was focused on studying galaxies, especially those that seemed far removed from our own Milky Way. Triggered by another astronomer's observations that these galaxies appeared to be moving away from us, Hubble deduced something groundbreaking. The farther these galaxies were, the faster they seemed to be moving. Initially, astronomers interpreted this as galaxies simply drifting apart. But as time went on, they came to understand this as the universe itself expanding. Think of it like being on a giant, uniformly stretching rubber sheet. No matter where you are on that sheet, you'd see everything else moving away from you, and the farther away something is, the faster it seems to be receding. This understanding was a monumental shift in our perception of the cosmos. It's like unraveling a grand puzzle where every piece, from the tiniest atom to the vastness of galaxies, contributes to this extraordinary story of expansion. The fact that this expansion rate isn't consistent across the universe adds an extra layer of complexity and intrigue to our quest to comprehend the cosmos. Advancements and discord in cosmic calculations. Hubble's initial estimations were based on the limited data available during his time, and since then, our ability to explore and measure the universe has significantly advanced, largely thanks to technological innovations. Telescopes like the Hubble and Gaia have become cosmic detectives, observing various factors and constantly refining their measurements. Other telescopes rely on cosmic microwave background radiation readings to calculate the Hubble constant. However, this method has its constraints, especially concerning the availability of supernovas for distant observations, limiting our view of the remote universe. In the 2 decades since the discovery of dark energy, scientists have been puzzled by a persistent issue. The measurements obtained from these different observational approaches don't align. They disagree on fundamental aspects, such as the age of the universe and the rate of its expansion. Despite technological advancements making measurements more precise, they've also unveiled minor inconsistencies. The quest for more sophisticated technology to resolve these discrepancies ironically tends to spawn even more questions about the universe's intricacies. Although the differences may seem relatively small, only about 10 to 20 million years, when considering a universe that's approximately 13.77 billion years old, these variations are worth investigating. However, reconciling these disparities poses a significant challenge. One proposed explanation suggests potential errors in our CMB measurements. However, measurements from instruments like the Planck satellite, responsible for these readings, have undergone extensive and rigorous testing since their release in 2013, affirming their precision and accuracy. Another perspective explores the tantalizing possibility of a gap in our comprehension of dark energy. There's a suggestion that perhaps dark energy isn't constant, but fluctuates over time, interacts with dark matter, or involves another unknown factor. This intriguing possibility has captivated theorists' minds, prompting numerous exploratory papers and theories aimed at unraveling this cosmic mystery. The search for answers delves deep into the fabric of the universe's fundamental forces. The discrepancies between measurements challenge our current understanding, driving the scientific community toward innovative theories and experimental pursuits. Exploring the dynamic relationship between dark energy, dark matter, and other potential cosmic influencers opens up a realm of possibilities, offering glimpses into the complex mechanisms governing the universe's evolution. Supernova measurements, while crucial in directly assessing the current expansion rate of the universe, aren't without their challenges. These measurements face scrutiny due to the intricate nature of exploding stars. If our understanding of the complex physics governing supernovas remains incomplete, it hampers their precision as reliable cosmological tools. Even a slight uncertainty or inadequacy in modeling supernovas could potentially resolve the entire discrepancy observed in the measurements of the universe's expansion rate. The James Webb Space Telescope, hailed for its promise of revolutionizing astronomy, has added a new layer of complexity to this cosmic puzzle. Its enhanced capabilities were expected to shed light on various cosmic mysteries, including those surrounding dark energy, dark matter, and the expansion rate of the universe. However, the complexity of the observations made by the JWST has introduced additional challenges rather than simply resolving existing uncertainties. JWST's Galaxy Formation Dilemma. Hubble's groundbreaking revelation about the universe expanding was anchored in his observations of galaxies. The James Webb Space Telescope, with its stunning images of galaxies forming much earlier than our current cosmological models predict, has ignited a crisis in the field. This particular challenge touches on galaxies' formation and their relationship with age and redshift. According to the standard cosmological model, hydrogen, a fundamental element, began emerging roughly 400,000 years after the Big Bang. This emergence occurred when protons and electrons combined. Before this event, protons and electrons coexisted, alongside what would soon become the cosmic microwave background radiation. Following the recombination of hydrogen, the universe predominantly comprised a smooth gas of these atoms, sprinkled with helium and residual background radiation. Within this environment, gravity could work its magic within perturbations, tiny regions of overdensity in the hydrogen gas. These perturbations gradually collapsed, birthing the universe's first stars. These early stars were composed primarily of helium and hydrogen, constituting the elemental building blocks of their time. However, this initial makeup was destined to change. The stars engaged in a process called nuclear fusion, a transformative process enabling the creation of heavier elements like carbon and nitrogen. These newly formed elements played a pivotal role in the formation of galaxies as they absorbed heat and emitted cooling photons, aiding the coalescence of gas into these cosmic structures. When these early stars reached the end of their lifespan and exploded into supernovae, they dispersed surrounding gas with these heavy elements. Each supernova and emerging black hole emitted ultraviolet radiation into the universe, stripping electrons from hydrogen atoms and enhancing transparency to UV radiation. Successive generations of stars continued this cycle, gradually enriching the universe with heavy elements and UV radiation. Over time, these elements and radiation reached sufficient levels, allowing vast quantities of gas to form galaxies. These galaxies became the gravitational hubs where gas collapsed, forming stars and other celestial entities. While observational evidence supports critical aspects of this narrative, challenges surface when integrating it into the cosmological framework of the expanding universe. The precise connection between the early formation of galaxies, the emergence of stars, and the overall evolution of the cosmos remains an intricate puzzle. Bridging these details into the broader context of an expanding universe presents a significant challenge for cosmologists and astrophysicists, urging them to refine and reassess our current models to better encapsulate these observations and their implications. Galaxies, defying the age-redshift relation. The standard cosmological model forms a crucial link between observed distances, conveyed through redshift, and the relative age since the Big Bang, expressed in years. These distances, once observed, are typically considered as unchanging, direct values. However, age emerges from theoretical constructs, combining models of an expanding universe. This framework, rooted in Einstein's general relativity and our understanding of matter from the standard model of particle physics, is designed to explain the correlation between distance or redshift and the duration since the universe's inception. the Big Bang. Yet a significant issue surfaced when the James Webb Space Telescope commenced its observations. As it peered into the depths of the cosmos and examined distant galaxies, it discovered phenomena that contradicted our current knowledge. Specifically, it detected galaxies much farther away and older than what the standard model predicted. While hints of such discrepancies were previously suggested by the Hubble telescope, the James Webb Space Telescope confirmed and amplified these findings. The crux of the issue lies in the discrepancy between the apparent age of the first galaxies and the predictions made by the age-redshift relation within the standard cosmological model. These newly observed galaxies appear to emerge far too early in cosmic history, challenging the limits of our current understanding. This anomaly directly challenges the chronological sequence we've constructed based on the age-redshift relation, suggesting that these galaxies shouldn't have formed at such early cosmic epochs according to our established models. This paradox implies a significant gap in our comprehension of cosmic evolution. It questions the fundamental assumptions embedded in our current models, signaling that there might be missing pieces in our understanding of how galaxies formed and evolved in the early stages of the universe. The foundational Big Bang model, portraying a universe in a constant state of evolution rather than a static, unchanging one, remains unchallenged in its broad strokes. However, the growing body of evidence in the form of new data continues to prod scientists to re-examine and refine this narrative. The question arises, how much of our understanding needs an overhaul, and what steps are scientists taking to delve deeper into these inquiries? In response to these complex puzzles, scientists are turning to more advanced equipment and methodologies to address these fundamental cosmic questions. One noteworthy endeavor in this quest is the Flamingo Project, an initiative within the Virgo Consortium. This project conducts extensive computer simulations, spanning the cosmic timeline from the Big Bang to the present, aiming to unravel the intricate evolution of the universe. The Flamingo Project utilizes detailed computer simulations to explore various elements of the cosmos. Funding for this ambitious endeavor has been secured from esteemed institutions such as the European Research Council, the UK's Science and Technology Facilities Council, the Netherlands Organization for Scientific Research, and the Swiss National Science Foundation. Through these simulations, intricate virtual galaxies and galaxy clusters emerge, providing a detailed understanding of how cosmic structures might have evolved over billions of years. Simultaneously, state-of-the-art telescopes like the Euclid Space Telescope and NASA's James Webb Space Telescope continue to gather invaluable data on celestial entities across the universe. The ultimate aim of these simulations is to compare the synthesized data with the observations collected by these cutting-edge telescopes. This comparative analysis will serve as a litmus test, offering insights into the accuracy of the standard cosmological model. By scrutinizing how well these simulations align with observed data, scientists aim to gauge the model's reliability in explaining the broader evolution of the universe. Professor Carlos Frank, an integral collaborator in the Flamingo research and the Ogden Professor of Fundamental Physics at Durham University, emphasizes a pivotal moment in cosmology. He highlights that cosmology currently stands at a crossroads where the data obtained from new telescopes doesn't perfectly align with our established theoretical models. This disparity raises critical questions regarding the validity of these models or potential biases within them. To address these discrepancies, precise simulations have become paramount. Previous simulations predominantly focused on cold dark matter. However, astronomers are now placing increased emphasis on incorporating ordinary matter, which constitutes a mere 16% of the universe, along with neutrinos, into these simulations to more accurately portray cosmic evolution. Led by Professor Jup Shea from Leiden University, researchers undertook extensive simulations to probe the universe's evolution. They utilized the Cosma 8 supercomputer, a component of the UK's Dirac high-performance computing facility, running simulations continuously for over 2 years. These simulations aimed to understand the impacts of both dark matter and ordinary matter, with a particular focus on the contribution of the latter. The complexity of these simulations demanded an enormous computational effort, requiring a staggering 50 million processor hours. To manage this computational load efficiently, the researchers introduced a new code named Swift. This innovative code was instrumental in distributing computational tasks across thousands of central processing units, enabling the simulations to run smoothly and effectively. At times, the simulations engaged up to 65,000 CPUs, showcasing the magnitude and complexity of the computational infrastructure necessary to delve into the intricacies of cosmic evolution. Now it's time for today's subscriber pick. According to Neil deGrasse Tyson, the James Webb finding ends debate in physics, shattering image, uncovering phenomena that challenge what we thought we knew about the cosmos, leaving us with the pressing need to reassess and possibly rework our scientific framework. However, the sheer magnitude of these revelations leaves scientists at a loss regarding where to even begin in restructuring our understanding. To comprehend the gravity of this revelation, let's revisit the early stages of the universe's development. Stars, black holes, and star clusters emerged relatively swiftly after the Big Bang, likely within a window of approximately 150 million years, potentially as early as 50 to 100 million years post-Big Bang. These cosmic events, though crucial, were expected to be relatively infrequent. The challenge lies in understanding the prevalence of evolved galaxies in the later stages of cosmic history, specifically between 200 and 400 million years after the Big Bang. Astronomers gauge the age of celestial objects by determining their distance from us, a technique rooted in cosmology. Recent images captured by the James Webb Space Telescope have revealed galaxies much farther away and therefore older than what the standard cosmological model predicted. This discrepancy between the anticipated and observed ages of these galaxies serves as another compelling piece of evidence signaling the need for a significant update to our existing cosmological model. Let us know your thoughts in the comments. Transformative shifts in understanding. It can be unsettling to witness our understanding of the universe undergoing a significant revolution. However, history has shown that our scientific comprehension has continually evolved through revisions and transformative shifts. Across the ages, humanity's perception of the cosmos has undergone remarkable transformations. In the early days of astronomy, Earth was perceived as the center of the solar system, with the stars and planets believed to orbit around it. This geocentric view persisted until the 16th century when Nicholas Copernicus challenged this notion, presenting a heliocentric model where Earth and other planets orbited the Sun. This groundbreaking idea revolutionized our understanding of celestial motion. Later, in the late 17th century, Isaac Newton's entry onto the stage ushered in a new era of scientific insight. His elucidation of the forces governing planetary motion, particularly gravitational forces, was a monumental leap forward in understanding the mechanics of the cosmos. As the 20th century emerged, Albert Einstein reshaped the scientific narrative with his general theory of relativity. This theory introduced a profoundly revolutionary concept, the unification of space and time. Einstein's theory, also known as the geometric theory of gravity, fundamentally altered our understanding of gravity. In 1915, he proposed that gravity arises from mass curving the fabric of space-time. Consider a massive object creating a depression in a sheet. The more massive the object, the more it curves the sheet. This curvature extends beyond influencing matter. It also affects light. Under the influence of massive objects, even light follows curved paths dictated by the warped space-time. This phenomenon, known as gravitational lensing, became a cornerstone of Einstein's gravitational framework. Renowned physicist John Wheeler summarized this interaction eloquently. Matter tells space-time how to curve, and space-time tells matter how to move. This encapsulates the symbiotic relationship between matter and the fabric of space-time, illustrating how the presence of mass shapes the very essence of the cosmos itself. Matter, light, and the curvature of space-time. The relationship between matter and the curvature of space-time governs the celestial ballet in our cosmos. This curvature isn't exclusive to affecting matter. It also influences light. When light travels, it follows a path known as a geodesic, which can curve in response to the curvature of spacetime. Picture a straight line on a flat sheet of paper. When the paper curves, that line is no longer straight. Similarly, the path of light, its geodesic, can bend when navigating through the curved landscape of spacetime. This bending of light around regions of curved spacetime created by massive objects is what we call gravitational lensing. Before Einstein's general theory of relativity, Isaac Newton's physics depicted space and time as unchanging backdrops against which universal events played out. Newton did foresee light bending, but to a lesser extent. Einstein's dynamic spacetime concept faced skepticism and demanded substantial evidence for acceptance within the physics community of the early 20th century. Gravitational lensing, observed and predicted, played a pivotal role in substantiating and cementing the credibility of general relativity. In the early 1900s, a profound debate revolved around whether the Milky Way constituted the entirety of the universe or was merely one among numerous star clusters. Edwin Hubble stepped into this cosmic debate by calculating the distance to a nebulous object located beyond the Milky Way. His calculations proved that our galaxy holds a modest position within the vast expanse of the universe. Building upon the foundation laid by general relativity, Hubble's observations of distant galaxies revealed a groundbreaking truth. These galaxies were receding from us, indicating the universe's expansion. It's worth noting that the Hubble Space Telescope, named after Edwin Hubble, but not the man himself, significantly refined these measurements, fostering ongoing cosmological exploration and studies. In more recent decades, the revered physicist Stephen Hawking proposed an intriguing concept. He suggested that while the cosmos might not be infinite, it lacks a well-defined boundary, akin to the surface of the Earth. Hawking also delved into theories concerning the potential end of the universe, adding further layers to our contemplation of the cosmos and its ultimate fate, unraveling the S8 tension in cosmology. The cosmos, adorned with brilliant stars and galaxies, holds a perplexing puzzle at its core, the S8 tension. This newfound challenge in cosmology revolves around measuring the homogeneity of the universe, specifically addressing uncertainties in its structural makeup. Despite the dazzling celestial displays surrounding us, understanding how matter is distributed across the cosmos remains a mystery, giving rise to this enigma known as the S8 tension. This tension arises from discrepancies in cosmological data, particularly concerning the lumpiness or distribution of matter in the modern cosmos. Efforts to unravel this mystery have coalesced around a groundbreaking computer simulation known as Flamingo. Unlike previous simulations fixated solely on dark matter, Flamingo takes into account ordinary matter and acknowledges its gravitational influence in the evolution of all cosmic elements. The universe's lumpy structure, characterized by the S8 parameter, poses a significant challenge. Astronomers gauge the precise measurement of this parameter through low redshift observations, such as weak gravitational lensing surveys. Gravitational lensing, an effect of spacetime curvature caused by mass, enables astronomers to study distant objects. However, a confounding disparity emerges between S8 values derived from cosmic microwave background experiments and gravitational lensing studies. The CMB suggests a higher S8 value, leading to what's now known as the S8 tension. It's important to note that this problem differs from the well-known Hubble tension, which focuses on discrepancies in the universe's expansion rate. The S8 tension is an entirely novel challenge in cosmology. Despite efforts using Flamingo's comprehensive simulations, which consider the impact of ordinary matter, including extreme processes like galactic winds, the S8 tension persists without resolution. The source of this problem remains uncertain. Some intriguing speculations have emerged, ranging from potential errors in measurements to the need for a re-evaluation of our entire theory on gravity. Simulations, however, have raised some perplexing observations. At low redshifts, the universe appears less lumpy than anticipated, challenging the predictions of the standard model. Yet, some measurements taken between low redshifts and CMB align perfectly with the standard model, hinting at a possible transformative shift in the universe's behavior over time. This tantalizing notion suggests that the universe might have adhered to expectations for a significant period before undergoing a substantial transformation. It's possible that while our current model may still hold partial validity, it might necessitate revision to accommodate these evolving observations. The quest continues to discern the extent of revision required, navigating the intriguing interplay between our established theories and the evolving nature of the cosmos. Would you consider the James Webb Telescope's discovery as a turning point in the history of space exploration? Let us know in the comments below. Thanks for watching, and we'll see you in the next one.